All right, how's everybody doing? Late again. Thank you, UNLV Internet. Any questions on anything? No? Annalito, you have... Oh, wait, he's not here, is he? Let's ask us. Oh, wait, Cassandra's not here either. All right, just so you know, I mentioned that you're not here. All right, war Kool-Aid on me.
Number 6 homework.
Number 6 homework. Oh, A20.6. Come on. Didn't you get well, let me tell you, are you hurting yourself? Did you get the email this weekend per the Google group? Okay, there's gold at my feet, but I have to bend over to pick it up. Oh, I'm poor. Seriously, I do all this, I respond to it, and now you're like, oh, I didn't even look at the gold. I mean, all right, so did anybody else not get the email?
I actually didn't get a notification. I just knew to look because I posted.
That's how you set up your preferences. You have to select that you get email immediately or you get a digest or whatever. New to Google Groups, huh? I don't know why I did poor on the quiz today. Seriously? And probably half of you don't even know what I'm talking about. All right, so let's do this problem. Oh, I'm looking at the schematic, so nothing interesting yet. You're going to have to remind me, this was a 20 by 2, and what was this one? And it's the 1 micron process. So we get, I'm going to call this voltage here, let's be different than what I wrote in the email. Let's call it V1 and V2. So just a sanity check for myself, what is VSG equal to? And what is VGS equal to? Right? Okay, and so would everybody be okay if I decided I didn't want to spend a lot of time on algebra? So what I wrote, well, I'm going to still spend time on algebra, but I can write that, well, tell me how to proceed. I know how to proceed, you tell me.
Equals VDD equals V1 minus 100 KI plus V2. No, VSG.
How about I need to keep it simple. So why don't I write ID is equal to or I write V1 minus V2 equals 10 to the 5th ID. Is everybody okay with that? Now I can write that, let's go ahead and I'll write it verbose like I did in the email. VDD minus VSG minus ID times 100K minus VGS equals 0. But I know this is equal to V2. And I know this is equal to VDD minus V1. So when I simplify this, what do I get? I get this equation, right? So it's not buying me anything. So why don't I write instead, I'm going to skip a step here and tell me if it's too much. V2 equals the square root of 2 times ID over Kp sub n times 20 over 2 plus V threshold n. I'm going to write, and I'm not going to skip this step, I'm going to write VDD minus V1, which is equal to VSG, is equal to the square root of 2ID over Kp sub n times P over 20 by 2 plus V threshold P. Looking good? Because I don't want you to say I don't know how to do algebra. I'm going to continue on, even though at this point I expect a 9th grader can solve this problem, because it's 9th grade algebra. Of course. The hell do I know? Oh, what a surprise. That's once. Okay, so let's write ID times 10 to the 5th right there equals V1 minus V2, which is equal to V1 minus V2. So V1 I can write as, moving this over, I'm going to, tell me if I skip too much algebra, but I hope not. Square root 2ID over Kp sub P times 20 over 2 minus V threshold P plus VDD. Is everybody okay with that? Minus V2, and V2 is this, so we get minus square root 2ID over Kp sub n times 20 over 2 minus V threshold n. Is everybody okay with that? Any questions? Okay, let's plug and chug. I don't know what ID is, right? But I'm gonna, since I've done this a few times, or actually, you know what? Let's pause and look at this for a moment, because so far there's been nothing that challenging, right? This would be a good quiz question, wouldn't it? Tell me, when I look at this, how can I simplify my life? Well, that's a number, that's a number. Let's do the easy ones first. 0.8, 0.9, 5. But what do I notice about this and this? No. They're exactly the same, except for this is going to be 1/3 of this. This is 40 and this is 3, right? So would everybody be okay if I said, I don't want to feel pain, so I'm going to use my brain before I start plugging in algebra here. And I'm going to write 5 minus 1.7 is 3.3. Then I'm going to put minus the square root of 2ID over 40 microamps per volt times 10 times 1 plus, I'm going to write it, no one's screaming it so I'm concerned. Does everybody follow that? See how I'm not feeling pain? That's 2. Now what? Well, what's that? I could put x equal to square root of ID, x squared equals ID. Is everybody cool with that? Then I can write And let's go ahead and write plus x, and then let's calculate what this is. Minus 3.3 equals 0. So let me see if I can do this in my head. So 2 over 40 is 1 over 20 micro, times 10 would be 200 micro, and that's square root. So let me see, square root of 100 is 10. Relax, man, you can turn it in later. Oh, all right. You called your name because I knew you'd appreciate that at the beginning of the video. Ringtone, ringtone. Is equal to, so what's the square root of this? What's the square root of 169? What's marked at 169? Nobody knows? Come on. Yeah, 13. So what's the square root of this going to be? Let's say 14. If I had a calculator, I'd do it, but I'm handicapped. I don't have a calculator. So would everybody be okay if I wrote this as 1 over 14? And I'm about to make a mistake. Save times 10 to the minus 3. Is everybody cool with that? So 14 times 14, let me see, that'd be 140 plus 4 times 14, which would be 40 plus 16, so that would be 56. 56 plus 140 is 196. Ooh, we're really close. We could say 14.08 or something like that, right? So now I'm going to write over here times 1 over 14 times 10 to the minus 3. But I don't want a mistake. So you know what I'm going to do? I'm going to multiply through by 10 to the minus 5. Actually, I could do something else here. I could say, now let's let x equal 10 to the 3 times x squared. Move this up. Would everybody be okay with that? Am I doing too much algebra magic here?
Did you take care of the 1 over root 3 yet?
1 over root 3. Where's that? Oh, I left that out. I almost made a mistake. Thank you for saving me, man. You saved me. Times 1 plus 1 over the root 3. What's 1 over root 3? What's root 3? Yeah, 1.7. Okay? So, should I continue or waste more class time, or can you plug that in the quadratic equation? Let's just, so I don't want you to say he can't do the quadratic equation. Let's set it up. 10 fifth minus, so that'd be x times 10 to the minus 2 times 1 plus 1 over 1.7 divide by 14 minus 3.3 equals 0. Let me see what this is roughly. That's going to be 0.6, say. So 1.6 times that would be 1.6. That would be roughly 1/10. So that would be roughly, very roughly, 10 to the minus 3. And then I write x equals the opposite of b, minus 10 to the minus 3, plus or minus the square root. If someone wants to calculate that exactly, we can see how off I am. B squared 10 to the minus 6 minus 4ac, which is minus times 3.3 over 2.
So you have that x squared times 10 to the 5th. So if you multiply by 10 to the negative 5th, that's
10 to the minus 5th. Yes.
okay.
Thank you. Keep me honest. Good enough? Does anybody know what this is? What is it?
That fraction itself is 11.3 micro. Is that to the 10 to the second?
Yeah, 10 to the minus 2. It's close enough, 11 versus 0.1 or 10. All right. Oh, okay, so then what? After we get the x, then we know x equals the square root of ID, so we square it to get the ID, then it's current mirror, we mirror it over, boom, we're done. Unreasonable problem, Worku? What's that? It's an unreasonable problem for a quiz? Yeah, but I have to explain it while I'm doing it. I'm handicapped. Plus, I keep wondering to myself, are they victims of poor algebra education because the Clark County School District couldn't hire good teachers? Oops.
Good thing you're not recording.
Yeah, ooh, wait. Yeah, we better check to see if we have evidence. Oops, where am I here? All right, any other quick questions? Because we need to get going. All right, everybody watched the lecture? Okay. So I want to do a quick example, and then I want to talk about the shortcomings. So if I do the following, and let's say that and let's call this VDS, and let's say VDS here is greater than VDS sat. What does that mean? It means it's in saturation. So this would be VGS minus V threshold N, correct? And this is the VGS. And everybody knows how to calculate the current flowing through here, correct? Okay. If I ask you now, just tell me what's the current that flows. If the current here is ID and these are the same size, what's the DC current that flows on this side? ID. Anybody not understand that? If I ask you, here's where I cringe, if I ask you what is the current ID AC that flows over here? It's not zero. I got an AC wiggle across the drain to source. And if you say GM, I'm going to start crying. You're going to see tears coming down my cheeks. You can take a picture and post on Facebook. Okay, what is the resistance I see looking down here? R out for AC, right? So when I say resistance, I'm talking about AC. So what's the current? Gee, you're not challenging me. It's VDS over R out. I apply a drain voltage. I get a drain to source AC voltage. It's limited by this R out. I model the transistor as a resistor in parallel with a current source, ID sat. And you say, oh, I remember that. Assuming we're in saturation and the curve looks like this, right from the beginning of the semester, I know that if I have a curve like this, I can model it as a resistor in parallel with a current source where the slope is 1 over R out. Right? Slopes in here correspond to resistors where the resistor's value is 1 over the slope. When do we have our first exam? If you didn't know that, you're not paying attention to the web pages. Boom, there it is. I don't want you saying that professor doesn't keep me updated on my grades or what's going on in the class. I was totally lost till the end of the semester and I didn't know what grade I was getting. You would never say that, would you? All right. Okay, good, because that's constantly what I thought when I was in school. I'm like, what the hell? And back then it was you didn't have an internet. You'd have to go to the professor's door and look for the grades, and then you'd be wondering when the grade's going to get posted, you know? And then they'd be mailed out, and you get them like 3 weeks after the semester ended. All right, so what we're going to do is we're going to try to increase the output resistance. Why is that? If we have a flat output resistance, what's that?
You get less of a slope.
Yeah, but why is that important? What if we have a slope like that, no output? What do we model this as? A current source. It's a more ideal current source. Does everybody see that? Okay, so I get a more ideal current source. Yay? All right, so I want a more ideal when I'm doing designs because then I have, we'll see later, higher gain, more ideal behavior, etc. That's 3. So here's what we're going to do. Well, first off, is this voltage here, this is my reference. Let's call this voltage V bias N. And we know that's equal to VGS. How does this voltage change with changes in VDS? Now, what am I the king of? You're not on your phone there, are you, man? Yeah, please don't. I have this ego that I think my lectures are important. And plus, if I was on my phone, I wouldn't be paying attention either. But you're in a good position, man. I couldn't see you. But I got to see, is he having pain? If he's having pain, I got to reduce it. All right. Of course, some people like this damn sense of humor. I don't like that. All right, so how do I, back on the farm, if VDS here changes, does that change the VGS? And thank you for answering. Sometimes I have, like last semester, I had people that are like this, and they've got it down here, like in the class, and I'm like, what the hell? And they're like, I'm not using my phone. I'm like, what do you think, I'm stupid? You're right there in front of me. All right, I told you what my daughter said, right? She says, you're mean. Yeah, okay. All right, so if I wiggle VDS, does the VGS here change? No. All right, but how do I keep the current constant then? Well, I can increase the output, but I mean, from a circuit point of view, if I want constant current, what do I do here? Keep VDS constant. But if I keep VDS constant, that means I can't change the voltage across the current source, right? So here's what we're going to do. We're going to do what's called cascoding. And your spell checker will say that it's a spelling mistake. And this is a vestige of a term called, from a common cathode driving a common grid. And that's from tube days, and so it's shortened to cascode. And in our terminology, this would be common source, and common grid would be the gate. So in a tube, when I was a kid, my parents' car had a vacuum tube radio, and so you'd get in the car and turn it on, and it would take a while to heat up. And even back then, that was pretty old. But tubes have an anode, which is like the drain, anode, and then a grid, which is the gate, and then the source, which was the cathode. And the reason they would take time to heat up is there would be a heater that would heat the gas in the tube, and then once the gas got hot, you could then modulate it, and you get transistor-like action, okay? So if you ever have to do tube stuff, you use the same knowledge. Just know that the grid, which looks like a screen, is the gate. The cathode is down here, that's the source, and the plate is the drain or anode, or the anode. So this is the cathode, which is abbreviated K, grid, anode, or plate. All right, anyway. So here's what we're going to do. I'm going to take and mirror over. So now when I calculate this current, what do I do different? Tell me how to write that current. Yay? See how easy that was? Because you have knowledge. You have savoir-faire. Any questions? So now I calculate the VGS. These are the same size. What's the current, assuming that's in saturation? Yeah, it's the same. Does everybody follow that? Questions?
So just a general question, because on the homework I kept kind of going back and forth on it and didn't get perfect understanding. But so normally when we have the same size devices and they have the same VGS, they're going to have the same current.
Yep, same size, same VGS, same current. Unless they're in triode or there's a significant
and that's what
output.
the resistor will normally do.
Yeah.
Okay, that's.
Does everybody get the constant point that this, throughout all, I'm going to do some fancy current mirrors. The VGS here and the VGS here mirror each other, correct? Does everybody see that? So that's what I'm going to be spending, or I'm going to be looking at. Now, I'm going to come over here, and I'm going to go look at this, and then as long as, well, let's see what the voltages are. What is this voltage here? VGS. What is the voltage here? No. VGS. All right, now, getting ahead of me. What's the voltage there? 2 VGS. So this voltage minus this voltage divided by R is the current. Okay, so what is this voltage here? What is this voltage here? What is that voltage? And let's see, this is VGS. So I drop down a VGS, and what is the voltage there? Looking good? Okay, so what's the minimum voltage? If I come over here and I ask, what is the minimum voltage I have here for current source? What's the minimum voltage I need across this device? VDS SAT. I gotta have the minimum. Wait, I'm not changing the voltage across this one. So this voltage has to be greater than VGS plus VDS SAT, which I can write as 2 VDS SAT plus V threshold N, because VGS equals VDS SAT plus V threshold N.
Why is either one have to be greater than VGS plus VDS SAT? I understand why it has to be greater.
This voltage is VGS, right?
Right.
So I need to have this voltage plus the minimum voltage across that.
Okay.
And then I ask, all right, well, how am I getting high? I'm going to do a sim in a moment, but I want you to explain qualitatively, how do I get higher output resistance? And when I say that, what does it mean in your mind? Higher output resistance, what does it mean? Flatter top. I don't ask complicated stuff. It means that line's flatter. Now, what's going to happen is we're going to see flatness until we get below this voltage. Then it'll follow the curve down of this device, because this will triode, and then it'll go down like this. Shall we prove it? Let's do a sim. Let's look at, let's actually look at examples in the nanometer process. So let's look at figure 2028. Oh, what's this circuit here? Oh, beta multiplier. It's the one we developed last time. Okay? Now I'm going from 0 to V out here, so I expect to see a curve that goes up. So I hit run. And I see there's my curve. And I see the horrible output resistance of the device. Tell me how to find that output resistance. Yeah, it's 1 over the slope, right? So I'm going to go like this. I'm going to say, oh, 1 divided by d of, so 1 over the derivative. Now, I'm going to get a number over here. This is going to be the channel resistance, and this will be the resistance R out in saturation, because in the channel resistance, that's in triode. Boom! And then we see that, oh, once we get above a certain value, remember last time or time before last, we said that, well, we enter saturation like right here. Look at, and we'll go back and look at the plot again in a second. Well, we'll enter saturation here, but look at how much changing the VDS changes the output resistance. Does everybody see that? Does everybody see how I found the output resistance? Of course, you have examples from the book that show this. Questions? Okay, so now I want to make, here, let's get rid of it. Let's close this. Let's rerun the sim. I want to make the output resistance flat higher. So I want to make this flatter. So I'm going to go use a cascode structure. So all I'm doing now is I'm using the beta multiplier. Here I've got it. I'm using the long channel process here to drive. So if I ask, just to make sure, because I'm used to looking at circuitry, if I ask what's connected to this node here, what sets the current here? Yeah, but what is it? What? Yeah, it's a gate voltage. It's a gate drain connected PMOS. I push down in here. There's my gate drain connected PMOS. That's how I'm getting the mirror out. Does everybody see that? Same old thing. Current mirror, gate drain connected. So I go over here, and then I've got my 2 transistors. I've got my cascode structure here. I hit run, and I look, and I go, holy crap, that's flat. See how flat that is? But wait, what happens right here? Yeah, the top device goes into triode because I don't have a large enough voltage. This top device goes into triode. I don't have a large enough voltage, and so then I just see the output resistance of this guy. So keep your mental picture there. Here, let's actually set the slope a little bit. Let's go, just to be consistent, let's do 22U. And the bottom, let's do 15U. Hit OK. Okay, so you got that curve there, 15 and 22. I'm going to get rid of the cascode, and I'm lazy. So I'm just going to put a wire across here so I don't have a cascode. And I could have also just deleted the device and reconnected everything, but this does the same thing. This will show what the output resistance is without cascoding. So we go in 22, 15. Everybody got a mental picture of that? So we hit run, and then we'll have to select, whoops. Oh, sorry, we need to plot the current in this guy because I've just bypassed it. So now we go 15 to 22U. And let's get rid of this trace because I don't have any. Does everybody see the difference? 15, actually, is it going to 22? Does everybody see the difference and why we use cascoding? Okay, but what's the problem? Problem is I have to have a larger voltage across my cascode structure. So I get a higher output impedance, but it's only at a larger voltage. Does everybody see that? So let's go back and think for a sec. Am I going too fast and everybody's like, too quick? So does everybody see that to have, this voltage here is what? Does everybody see 2 VGS? I got a VGS and a VGS. So this is 2 VGS, and so this voltage is VGS, assuming we're in saturation. So I need a VGS here plus a VDS sat here. So I need a VGS plus a VDS sat. Yeah, to keep everything in saturation, to have that real high cascode output impedance. Does everybody follow? So that's a problem, right? What I prefer to have is a VDS sat across here and a VDS sat across here minimum, because then I could go way down here before my impedance started to fall. Does everybody follow that? So I'm going to change this topology, but before I do that, I'm going to derive what the new output resistance seen looking in here is, because this is one of my favorite testing quiz questions. Okay? Before I do that, if I apply an AC voltage here, what's the AC voltage there? If I apply it at the drain? 0. I'm not changing the current through this side. The voltages on this side aren't changing. What's the AC voltage there? So I'm going to go from DC to AC. Everybody cool with that? Okay, so I'm going to redraw the schematic. What is the AC voltage here to ground if I apply an AC voltage over here? 0. Okay, so let me redraw or re-say everything I said here, because I'm a firm believer that you have to say things more than once. Is that true? No! Say it once, we got it! Okay, so here we got, why don't I put a current source in there, which we know is the PMOS going to the beta multiplier. And then let's apply a voltage here. This is my constant current. Refresh my memory, what is this? Where is this point in the schematic? What's the voltage in this schematic of this point, DC? And where is it? Any questions? If I have a constant current flowing through here, I have no AC over here. The only AC I have right here is this Vx. What's the AC voltage here? And what's the AC voltage here? Okay, so now I'm going from a DC schematic, I'm going to draw an AC schematic. Is everybody cool with that? So don't go, hey, you got 0 volts there, that device has to be off, because wait, we've just changed from DC to AC. So I go over and I write, all right, here's my schematic for AC. Hey, wait a sec, you don't have a big enough voltage across those. Stop. We're doing AC. You can tell I've been teaching and I know what students think. All right, it's AC schematic. Okay, so I'm going to redraw this schematic using the small signal models. Here's my Vx. There's my R out N. There's my GM VGS, whatever, we'll call 2. Here's my gate for the top device. What do I connect the gate of my top device to? And then here's the source. So isn't this voltage here VGS2? Any questions? So this will be something easy you get when I give you a quiz on Thursday and say, show how to derive the output resistance of the Cascode. And you go, he's not challenging me. Okay. So then I come over here and I do the same thing. R out N, GM VGS1, and then let me see, gate is here, goes to ground, and then I got plus minus VGS1. Tell me something useful here. What's VGS1?
They're zero, so both of those current sources are zero.
Wait, this is 0, right? Does everybody agree? This is at AC ground, this is at AC ground. So wouldn't you agree this is 0? So what's 0 current? We remove it, it's an open. Is everybody cool with that? But wait, this voltage isn't going to be, this one isn't going to be 0 because I'll have whatever the current flowing through here is, we'll call it IX, will come and flow through here. So there's a trick. There's 2 tricks. I'm going to do it on the next part. The first trick is to realize these are at ground, so the bottom device VGS is 0. So you replace the bottom device with just the R out. Does that make sense? The second trick is that when you're determining the input resistance of anything, there's my eyeball there, it's Vx over Ix. Second trick is to realize that the current, that water that flows in here has to flow out through here. So this voltage is what? This is the second trick. So you need to remember these 2. It's no auto voltage divider. Don't think deep. What do I don't ask complicated questions. Yeah. Ix, the water that flows out, times R out in. Yay? Cassandra, is that? Oh wait, she's not here. That's right. Joke never gets old. I should tease her and say, can you get us some discount tickets to the best show on the strip? All right. Shall we continue? So I'm going to, on the next page, do the following, because I like neatness. Does everybody agree with what I just wrote? Whoops, let's call it X to be consistent with the previous slide. And then R out of the cascode is equal to Vx over Ix. Stop and stare for a moment and ask me questions.
R out of the cascode, that's the impedance of the main.
Yeah, that's the flat area there.
Right, but then the voltage between the 2 resistors is Ix times R.
All right, you're getting ahead of me, but let's write that down. So the current, that's one of the tricks. So I already removed this bottom current. This current's what? What flows in has to flow out. This voltage is, and therefore VGS2 equals minus Ix times R out in. Oh wait, it's 0 minus this voltage, which is Ix times R out in. Questions? Good quiz question on Thursday, right? Show how to derive the output resistance. Sketch the schematic of a cascode. Show how to derive its small signal output resistance.
So what about the GMVGS?
Hold on there, big fella. Am I going too slow? I'm going to do it. I need to make sure that everybody, I don't want you to leave the classroom and say, he's not only mean, he teaches crappy. I don't care if you say that as long as you go to a job interview and you do well and get the job. All right, so tell me what to do now. Well, you can, but I'm assuming we did that already because we calculate the DC values and all that, so we can calculate the GM. So tell me what do I after here? I know what Vx is my input, but I need to find Ix, right? So here's the way I can do a KCL here or a KCL here. It's basically the same thing. So why don't we, this first time I derive this, what do you want to do, top or bottom? Let's do it on the top. So would everybody be okay if I wrote Ix is equal to GM VGS2 plus the current that flows through there? What is the current that flows through there? Vx, this voltage, Vx minus this voltage, which is divided by and I'm after this, right? So why don't I, and VGS2 is equal to minus Ix times R out N. So why don't I move all the Ix's on this side and write Ix times 1 plus what? 4. Is everybody okay with that? Now what? Is everybody okay with that? Tell me you're okay. I need some life. I need some passion. Did I make an algebra mistake somewhere? Let's see. Ix equals GM VGS2, yay, plus Vx minus Ix R out N over R out N. Let me go over, well, let's see what the answer is in the book. It is on page, oh yeah, equation 2053, we're right on. It's equal to 2R out N plus GM R out N squared, which is approximately GM R out N squared. So our basic Cascode had an output resistance of R out. Our basic current mirror had a output resistance of R out, but now we have R out times R out. This is our Cascode. So we went up by the, what do we call this term? Open circuit gain. All those things we keep going over and over, using over and over again. So by using the Cascode, we get an increase in the output resistance of the open circuit gain. So if the open circuit gain was 100 and our output resistance was 100K, now we're at 10 meg output resistance. Any questions on this? Is this a reasonable quiz question? Especially since I told you. What about PMOS? Could you do the PMOS? No? Okay. Try it on your own and then ask me next time if you can't do it, and I'll do it for you. And I'll show you how fast I can do it just for fun. Alright. Let's cover one more thing and then we'll have our quiz. How's the pain factor? Pain factor good? Are you learning anything? Is the homework good? I had 2 students tell me that in their other classes they're not getting enough homework, and my response was, are you getting enough homework in my class? Oh yeah, that's what I like. Okay, so here's my cascode structure, and for minimum voltages, what do I need for minimum voltage for my cascode? VDS sat. Does everybody agree for minimum? So then this voltage has to be greater than 2 VDS sat. So I'm going to ask easy questions, so don't blow it. What's the voltage here called? Okay, you don't modify this because that's how much you're turning the valve on. Okay, you're not playing games with that. What's the voltage here? Again, I don't modify that because that's how much I'm turning the valve on. They've got to be VGS. So I can come over here and I could do the following. Is everybody cool with that? And there's my current mirror for this guy. Now I need to figure out what to apply here. So what's that voltage now? Notice when I say what's the voltage on the note, it's with reference to ground. What's this voltage? One more time. Okay, so one more time, what's that voltage? The current that flows through here is ID. Current that flows through here is ID, assuming these are in saturation. What I want to do is I want to get a device here that's gate drain connected. And let's drive over like that. But I want to size this device. Let's call it W wide swing over L. I want to size this device so that I can have a larger voltage here. Wide swing means that I can get a very small voltage across the Cascode's current sink and it'll still operate. So all it means is instead of having that larger voltage, I can now have a smaller voltage. Is everybody cool with that? And the current that flows is ID. So I need to figure out how do I generate a VGS wide swing, which is equal to the VGS of the other transistors plus VDS sat. But wait, what is VDS sat again? So what that means is I need this voltage to be equal to 2 VGS minus a threshold. Am I losing anybody? Anybody hear the lecture behind us? Dare me to pound on the wall? Turn that racket down. All right, so I'm going to go do the following. I'm going to write ID, which is the current flows through here, is equal to my Kp sub n over 2 times W wide swing over L. I'm going to assume the same L is used in everything, and I'm going to assume all the other transistors are W over L, times this VGS. So times 2 VGS minus V threshold N minus V threshold N squared. Would everybody be okay if I factored out the 2? So it would be 4. And so I get the following. I get Kp N over 2 times W wide swing times 4 over L times VGS minus V threshold N squared. So let me come back to this for a second. What is the current here equal to? What is ID equal to in terms of VGS and W and L? Does everybody agree with that? Well, wait a sec. These are exactly the same, except I have this W wide swing is times 4 would be equal to the W here. So I can write W equals W wide swing times 4, or W wide swing equals 1/4 times W. So if I make this guy 1/4 times the W, I can get wide swing operation. So why don't I do that? So wait a sec. Let me go over here to the schematic. And what was the one we were just doing? It was, oh, this one, right? So let me ask a question. If let's go ahead and modify this schematic real quick. And then let's go get the scissors out here. And let's make it exactly what we had. Coming down. Let's do a little copying. Let's move this up. Let's do a little stretching. And let's do a little moving. And didn't move it enough. And then let's actually connect this over. And then let's get out the scissors. And, oh, you see what I did? Okay. And then let's go over here. If I make this 1/8 or 1/4, I make the L larger, and I hit fit. Tell me what that does to the voltage here. If I make that longer L, what happens to the voltage right here? If I keep a current, okay, forget the circuit for a moment. Let me just pretend we're in the supermarket and I'm asking you a CMOS question because you need your brain flexed. If I keep the current through a MOSFET constant and I increase the length, what happens to its VGS? Okay, let me ask you a simpler question. I have a hose bib and I keep the current flowing through that hose bib constant. But I reduce the diameter of the hose bib. What happens to the pressure drop across the hose bib? What happens if I reduce the pressure or the diameter to 0? What happens to the pressure drop? Goes to whatever the supply is, right? I can't get anything through it. The current goes to 0. So if I have a device and if I have a pipe and I reduce the diameter of the pipe, what happens to the pressure drop along the pipe? Say you have a garage and you want to run yourself some air tools. So you get some PVC pipe. You look at it, I could get 1/2-inch PVC pipe to run the air, compressed air, or I could get 1 inch. Which is going to be more effective and drop less pressure from your compressor to your air tools? The bigger one's going to drop less pressure, right? So if I increase the length, what happens to the pressure drop? So if I make it 100 feet long versus 50 feet long, what happens to the pressure drop from one side to the other? Yeah, increases with length. So if I keep the same current flowing in here, but I increase this length, what happens to the pressure drop? Goes up, right? So I expect this voltage to go up. Before I had 2 VGS, now I'm going to have VGS plus a VDS sat. I'm going to go over this again when we meet. Remind me next time, because I'm seeing a bunch of... Boom! Look at that. See how flat that is? See how it doesn't go into triode? It's nice and high impedance for the whole way. basically we keep the two VDS across and we got like a nice perfectly constant current that flows, and we've designed a good current source. Cascoding is incredibly important in analog IC design, and it's hard to find any analog IC that doesn't have a cascode current mirror in it. Okay? Not just in CMOS and bipolar as well. There's bipolar cascode current mirrors as well. Let's stop here. Make sure you have your questions.